Hey everyone, my name is Erin McCarn and I'm a grad student in the Subramanian Research Group in the Chemistry Department at OSU. So in my research, I make and examine the properties of new pigments, semiconductors, and dielectric materials. A little bit of background about me. As an undergraduate student, I started as an art major my freshman year, and I wound up graduating in chemistry. During that time, I was absolutely infatuated with nanomaterials, so I'm excited to share a little bit of what I know, and I hope you're ready to get a little nerdy with me. In the text Information Arts, Wilson combined chemistry and materials science under the same introductory description. As a materials chemist, I feel it's important to make this distinction. Chemistry is the fundamental study of matter and its changes. When you get into practical applications of chemistry and how a material may be used on its physical and chemical behaviors, it becomes material science. There's some important questions to ask about nanomaterials. The first being, what does nano mean? Nanoparticles or nanomaterials are any objects measuring between 1 and 100 nanometers, so effectively most anything between 1 millionth to 1 billionth of a meter in width. Why are nanomaterials special? Their size allows them to exhibit both quantum and Newtonian physics, giving rise to novel physical, optical, and electronic behaviors. Quantum theory generally applies to the very small, atomic scale. Newtonian theory applies to bulk matter, so large bodies, everyday things. Additionally, they're highly tunable and can be made into a wide variety of shapes from unknown numbers of combinations of elements. But what's the downside of nanomaterials? Most have a heightened risk for biotoxicity. As it turns out, nature and cells really like doing and using things at the nanoscale, which when used appropriately can be great, but when used not appropriately can be detrimental. How are nanomaterials used in science? Smartphones, fabrics, anything you buy these days that boasts antimicrobial or no odor likely has silver nanoparticles embedded in it. The upside is they're great for their disinfecting odor stopping action. The bad news is they're being manufactured, used, and leached into the environment more than ever before. We have no idea how this could affect the global biosphere long term. In the image in the upper right, here you can see some lipid-coated gold nanoparticles I synthesized during my research rotation in the Makiavix lab group here at OSU. The Makiavix group specializes in the synthesis of noble metal nanoparticles for use in the biological theranostic applications and the detection and treatment of cancer, macular degeneration, and neurodegenerative diseases. The particles they synthesized have an approximate average diameter of 50 nanometers, evidenced by their ruby red color. Once gold nanoparticles reach a diameter of about 90 nanometers, they exhibit a bright purple color in solution instead of the ruby shown here. Quantum dots, shown on the left, are nanoscale semiconductors. Cadmium selenide and cadmium telluride are the most explored quantum dot systems and are known for their bright array of fluorescent colors and tunability. While this technology is exciting in the world of medical imaging, it's found its way into mainstream tech as well. Quantum dot televisions and monitors are now at the cutting edge for digital displays due to the unprecedented crispness and brightness of blue hues that were not achievable with previous TV technologies. We talked about the present, but we are nothing without our pasts. I want you to imagine the ages of alchemy, where the fastest means of communication was by word of mouth and conventional wisdom was largely passed down through oral tradition. The scientific revolution had yet to come, and the cause of disease was due to a moral or ethical trespass. Ancient Greek literature, studied and pored over by the alchemists the world over, implicated the creation of a sorcerer's stone, ruby in color, that would be the key to transmutation of substances into gold. The earliest record of gold ruby glass appeared in 10th century Persia. The recipe for gold ruby glass was lost and found countless times, supported by archaeological evidence of its appearance and disappearance throughout time until its heyday between 1685 and 1705, whence the scientific revolution demystified its creation. Conventional soda-lime silica glass is a mixture of sand, potash, and soda ash and was originally made by combining sand, ground seashells, and wood ash. Iron is a common impurity and produces everyone's favorite Coke bottle green. But red is a little trickier. The glass artist must add some solid gold chloride to the mix. When this happens, gold is in its +1 oxidation state and is colorless. The gold ions mix in with the hot glass at about 2000 degrees Fahrenheit, and the desired object is then formed by the artist. The glass is cooled to a lower temperature and then reheated for a second treatment in an oxygen-devoid environment, otherwise called a reducing fire. This process is known as striking, and this is what is known as a striking pigment. When this happens, the gold ions gain an electron and become metallic gold. The metallic gold particles can easily slip around in the glass matrix and find other gold particles. They clump together to form aggregates. The size of the aggregates determines the color. Just like my particles in the lab, the ideal size is around 50 nanometers for ruby glass, as seen in this German-covered goblet. However, if the artist heats the glass for too long, the nanoparticles get too big and the glass becomes opaque and liver-like in color. Now, if you're like me, you're asking, why are small particles of gold red and large ones purple? As a scientist and as an artist, one of my favorite questions is why are colors? So here we go. Absorbance refers to the absorbance of light, which is opposite from reflectance. Black absorbs all light, white reflects all light. A reflectance of purple, like with the 90 nanometer gold nanoparticles. What we visually see is due to the absorbance of yellow. When yellow light is absorbed, we observe its opposite counterpart, purple. UV visible spectroscopy allows us to determine the exact wavelength of light absorbed with more accuracy than the human eye, giving us a better understanding of color as it relates to the world as a whole. It turns out there's a lot of interesting quantum physics involved in color theory. If we look at the UV vis spectrum in the bottom right corner, we see an absorbance for the 30 nanometer nanoparticles at a wavelength of about 540 nanometers. If we look at the spectrum, we see that this is an absorbance in the green region, which correlates to a reflectance of red. What's happening physically is when the spherical nanoparticles interact with a wavelength of light, it causes the electrons on the metallic surface of the gold nanoparticle to swing back and forth like water sloshing in a cup. This lively group of collectively sloshing electrons is called a plasmon. When everyone in the plasmon is sloshing at a predictable rhythm, it's called resonance. Electrons on the surface of larger particles slosh more slowly than smaller particles. The slow sloshing causes absorbance at a lower energy and longer wavelength of light in the yellow region, where the electrons on the smaller particles slosh more quickly and absorb more energy at the shorter wavelength in the green region. So you're not just seeing red, you're seeing quantum physics. And for my last trick, I'll tell you about DNA origami assembly of nanomaterials. The scientific world was shocked when this image appeared in 2006 of a smiley face, 10 nanometers in diameter, made by manipulating DNA. To create these intricate shapes, researcher Paul Rothman took long circular strands of DNA and stitched them together using short strands of DNA called staples. He stapled together the long strand into intricate shapes and designs to create various nanostructures with the DNA. Researcher Lior Cipinaru of the University of California presented his work at a chemistry seminar this past spring. He and his group used DNA origami to assemble new metal structures. They found that silver ions fit between the base pairs in their DNA structures. They would then reduce the silver ions by adding an electron and creating metallic silver. The silver particles stuck in the DNA strand would cling to their neighbor silver particles and form a silver nanowire, opening up an exciting new world for nanoarchitecture. I hope I've managed to blur the line between science and art just a little more for you all. Thanks for listening and stay curious, friends. And for a couple of great songs inspired by chemistry, please go to these YouTube links.